Unit 8. Reading 1.
The Tacoma Narrows Bridge Collapse and the Lessons Learned. Suspension bridges are amazing structures. They appear fragile but are very strong. They are relatively light and flexible. This makes them ideal for long crossings, but susceptible to wind, causing them to vibrate and move both vertically, up and down, and laterally, sideways. It was a mixture of these elements, lightness, flexibility, and wind, as well as a forgotten lesson learned that led to one of the most famous bridge failures in history, the Tacoma Narrows Bridge Collapse. The Tacoma Narrows Bridge. When completed in the summer of 1940, the Tacoma Narrows Bridge was the third longest suspension bridge in the world, with a center span of 2,800 feet and a total length of 5,979 feet. For comparison, typical center spans range from 2,000 to 7,000 feet, and the longest suspension bridge in the world today is the Akashi Kaikyo Bridge in Japan, with a center span of 6,527 feet and a total length of 12,828 feet. Like other suspension bridges, the Tacoma Narrows Bridge had a roadway, called a deck, suspended by large cables. The cables were anchored at each end of the bridge and passed over the top of tall towers built onto piers. The deck was attached with suspender cables, and its weight was supported primarily by the towers. However, unlike its predecessors, the Tacoma Narrows Bridge was just 39 feet wide, allowing for only 2 lanes of traffic. After the bridge opened, many drivers drove it not for the convenience of crossing over Puget Sound, but for the experience. When moderate winds blew, the bridge would sway from side to side and sometimes even undulate. On windy days, the sensation was so pronounced that drivers reported that the car ahead of them would sometimes disappear and reappear several times as they crossed the bridge. People compared the bridge to a roller coaster, and it was given a nickname, Galloping Gertie. Because of concerns about the movement, University of Washington engineering professor F.B. Farquharson and his engineering students were hired to try to stabilize the bridge. Ultimately, however, their efforts were unsuccessful. The bridge collapsed on November 7, 1940, just 4 months after it opened. Fortunately, there were no human fatalities. Only a dog that wouldn't leave a car died when the bridge fell. The last people on the bridge were Tacoma News-Tribune photographer Howard Clifford and Farquharson. They ran off the bridge just as the center span finally broke off at 11 a.m. Dramatic video shows the bridge twisting violently in the wind and eventually falling into the water. Why the bridge failed. The bridge's failure led to a decades-long attempt to understand the effect of wind-induced motion on suspension bridges. At the time, engineers concluded that the cumulative effect of undampened rhythmic forces produced the motion that ultimately caused the bridge to fail. For years, that idea prevailed, specifically that the collapse was related to resonance, a phenomenon that caused the wind to resonate with the natural frequency of the bridge's structure, resulting in a steady increase in amplitude until the bridge was destroyed. This explanation and the film of the collapse were widely used in physics classes to demonstrate resonance. Today, most engineers disagree with that explanation. They believe that aerodynamic instability caused the bridge to fail. In studying the film and other evidence, they believe a cable slipped and the bridge's motion changed from vertical to twisting. The deck, too narrow, light, and shallow, continued to lift and twist. This in turn caused the wind to split around the bridge, which created a swirling pattern that further lifted and twisted the deck. The bridge went into a self-induced vibration. The forces acting on the bridge were no longer caused by the wind, but rather became self-generated. Its twisting generated more twisting. Eventually, this motion resulted in the deck breaking and falling. This vibration, called torsional flutter, is the most probable explanation of the bridge's failure. In other words, the bridge was too flexible, both vertically and in torsion, twisting. Due to its width-to-length ratio, 1:72, the bridge was not resistant enough to twisting forces. Today, no suspension bridge has a ratio greater than 1:47. Lesson learned. The story of the Tacoma Narrows Bridge can be seen as a lesson learned, forgotten, and then relearned. Engineers in the late 1800s appear to have known that suspension bridges that were too light and too flexible would fail, and so they built bridges heavier and stiffer, like the 1883 Brooklyn Bridge. But that lesson apparently was forgotten, as J.K. Finch suggested in his summary of suspension bridge failures published soon after the Tacoma Narrows Bridge collapse. The failure also shows that aerodynamic forces were not well understood. Today, wind tunnel testing of bridge designs is commonplace. In 1950, a new Tacoma Narrows Bridge was built, featuring a wider roadway, deeper and stiffer supports, and features to dampen the effect of the wind. That bridge, along with hundreds of other suspension bridges around the world, still stands today and is hopefully proof that lessons have been learned.